Um, no, I don't know. Whoa, this is way more. Oh, and I'm recording. Gotcha. There we go. All right. Oh, look, we could probably keep the lights on. Yeah, it's like, we should just like hold class down here, right? We'll see. Okay, so I was just talking about Levene's equality of variances test, everybody's favorite variance test. And what I was saying is that usually, like, you don't have to know a ton about it, just that one of the assumptions of independent samples t-tests is that both of the groups that you're comparing are similar, meaning like they have similar numbers of people in them and they have similar variability about the mean. So it's not like one has tons of variability and the other one has a little bit. If it does, Levene's test for equality of variances will like correct for that and give you a whole other row of information that you need to report. So it's cool. So I just wanted to give you an example of what that might look like. So up here at the very top, you'll see we have our Dundee and Exarban groups. And you'll see these are the same groups we've been talking about the whole time, right? So we've got our mean of 25 and then our other mean of 20. So these are the groups we were looking at the whole time. And when we look at their standard deviations, we see that they're pretty similar. This group has a standard deviation of 11.29. This one has a standard deviation of 10.51. So they're not even 1 point different. So they have pretty equal variability, right? And so when we look at Levene's test for this group, these two groups, we see that it's not significant. And that's not surprising because they're not that different. So it's basically saying, yep, you met the equal variances assumption. It's fine to proceed with this line for equal variances assumed. So you can read all the stats on this top line. Now to just kind of contrast this so it makes a little bit more sense, if you look down here, let's say that, all right, we grabbed a different group. We grabbed another group of Dundee kids and another group of Exarban kids to compare. So here's our new Dundee kids. Here's their mean. So they have the same mean. Here's our new Exarban group. They have a little bit higher mean. That's not a big deal, but when you look at their standard deviations, you can see that the Dundee standard deviation, it's our same standard deviation. The Exarban group, no! We don't have to right now. There, okay. Our Exarban group has a huge standard deviation. It's like 28. It's humongous. So there's, for whatever reason, the answers these kids gave in this Exarban sample are all over the place. So they vary a ton. And so we can see, like, when we compare these, when we eyeball the standard deviations, there's like 16, 17 points difference. It's huge. So when we look down here at Levene's equality of variances, we see that this test is significant. So we have a significant test of the Levene's test, a significant test. And so that is saying that our variances in the groups are significantly different. They're way different. They're significantly different, and so our equal variances assumption that's not met. So if this Levene's test is significant, it's basically saying drop down and read that second line of information. So again, what's cool is that doesn't have to stop you. It just means you have to read the corrected version of the test because it will correct for that, but you have to read the right row if it did correct for it. All right, any question on Levene stuff? Okay.
I do have a question.
Yeah.
So with Levene, you can or cannot have the same N. The same sample size.
You can. You can have slightly different sample sizes,
okay.
And if it's a problem, it will tell you.
Gotcha.
Yep, because your sample sizes will probably affect your variability too. And if it's not a big deal, it's not a big deal.
When did you say they had to be the same?
They're supposed to be the same. You want them to be close to being the same, but if they're not, that's what you'll want to check and make sure it's not totally messing up the results of your test.
Okay. And you use Levene if it starts off it's not significant.
Right, so if Levine's is not significant, it means you're fine. They're not different. You can go ahead and proceed with the test as you assumed it would be,
So
right?
you want them to not be significant.
Exactly, yes. It's another one of those, you want it to not be significant. Because significant means you violated your assumption that your groups are different, that your group variances are different, and then it has to correct for it by using that bottom row.
And what's the number that we use for significance?
0.05.
0.05
Yep,
across the board.
across the board, which is nice at least. So sometimes what happens is students will accidentally see this test and assume that's the F value and the significance, like that they think this is whether their test is significant or not, and it's not. This is a test of whether you can proceed with the test as normal or if you have to use the corrected version. So it kind of comes first because it's like SPS's way of being like, hold up. Before you just look at these answers, you need to make sure that this very serious assumption was met. If it wasn't, you have to look somewhere else. You have to look below to the corrected version. All right, any more question on Levine's? Let it sit for a second. Okay, so let's go here. So
the
yeah.
variance is different. If it's significant,
Right.
it is different.
Yes, you got it. I know it's weird to wrap your head around, but yes. If it is significant, it means your variances are significantly different. And that's bad. So you have to drop down and use the corrected line. So you have to use this bottom line here. I mean,
And that's the equal variance.
Equal variance is not assumed. So it's basically saying, I can't assume that my variances are equal, so I have to use this corrected version. And you'll see the only difference is your degrees of freedom, really. Right? So like these all have about the same values, but it's really just adjusting for that difference between your groups. So it's adjusting these degrees of freedom.
So that significance right there is based on p-value.
Yes. That's what's weird. So this is your p-value.
Okay.
Yep.
That is our p-value.
That is your p-value. What?
What is our p-value?
This, right? Where in SPSS it doesn't say p-value, it just says sig. And that means that is your p-value. So instead of saying p is less than, it says p is 0.004. It totally calculates it for you. Exactly.
So the 0.990 is significant also?
No,
It's not.
because it's way bigger than 0.05.
Right.
So it's weird. It doesn't like say, yes, it's significant or not. It's like, here is your value. You have to decide whether it's significant or not. And if it's less than 0.05, yes. And if
Okay,
it's
so that one's less, and that's what.
exactly, yep. So this one is the one that we're actually using because our standard deviations are not that different. So we can meet this equal variance as assumed because we know that our Levine's test is not significant.
So then we can just stop there.
So yep, then you can proceed to here,
Okay.
which we'll do
And then
in
we
the
don't
next
have to go down.
Yep, you don't have to go down. So the way I always try to remember it is like, if it's significant, drop down and read these, report these statistics.
Okay.
If it's not significant, proceed as normal.
And then you go down to the bottom column, which is where you will talk about the equal variance.
Let's see, so bottom column, like
The very bottom chart.
this. So don't worry about, so this is it might be a little confusing. These are two separate comparisons.
Oh.
So you won't have these two. This was basically just to show you like,
Oh, the bottom row right below it.
right, this, yes, so you can ignore this, sorry. So if this is not significant, you can ignore this bottom row. If it is significant, read the bottom row. It's a lot of little stuff to keep track of. Okay, so we'll go ahead.
Can I ask you one
Yeah,
more time?
Yeah, no problem. Yep.
Based on the top one, is that significant or not?
It is
It's not.
exactly. It is
It's
not
not.
significant.
This one is.
Yep,
because it's-
exactly. So these are just to kind of show you why you would get a significant test, and this because the standard deviations are crazy different.
Okay.
And so luckily, this is our sample up here. This top one is what we'll actually be using. But in case you wanted to know what is going on with this variance is assumed thing, this Levine's test thing, this is when it would become important, is when you have unequal variances, when things are really different. And what's awesome is, again, SPSS totally corrects for that and gives you that information anyway. You just have to know based on these values which line to read.
So the second example.
Yeah.
It is significant.
Yep.
So you drop down, look at the next column.
Right. This next row.
And
Yep.
then what do you look at from there?
So that's what we'll look at right now. So basically, that Levine's test just tells you which row to be reading. So this is the rest of that table, right? So if we looked originally, right, here's our table, and we had the two yellow boxes. The first box is about Levine's test, which we just talked about. The second box is our actual t-test for equality of means. See how it says that on top? So it's weird. This is where the meat of what you're looking at is in this t-test for equality of means. That's what you really want to pay attention to. And so if you look at this part of the table, you'll see that you have your t-value for your group differences. So here's your t-value. Then you also have your degrees of freedom right here. You have your p-value for your significance level for your test. And so this is where all the information you're interested in is at. So the reason you have to look at Levine's first is because you need to know which row to look at. But after you figure out which row to look at, this is where the information you really want is at. So a couple things to note about this output. The degrees of freedom is calculated differently for an independent samples t-test than it is for a one sample t-test. So basically for each group that you have in the test, you remove 1 degree of freedom. So in a one sample t-test, our degrees of freedom was n-1, right? In a independent samples t-test, we have 2 groups. So our degrees of freedom is n-2. So you just subtract the number of groups. And you can see that that's what's happened here. So we have 2 groups of 22. You add that up. That's 44 total people in our test. Minus 2 for the 2 groups is 42. So that's how you calculate the degrees of freedom for this test. The other way you can look at it is like it says on this formula down here. The n of group 1 plus the n of group 2 minus the number of groups. So that's one thing to note is that the degrees of freedom are slightly different for this test. Another thing to note is your p-value, the significance of your two-tailed test right here. And what does this p-value tell us? It's greater than 0.05.
So it
Pennies with a
So it
decimal.
is significant.
Is it 0.099?
It's not significant because it's greater than 0.05 because it's 0.09. Yep, sorry, I know, I guess I'm like you guys, you can't see it as well as I can see it right here on my screen. So this is not significant. So it's saying our p-value here is larger than 0.05. There's not a significant difference between the Dundee classroom average January temperature guesses and the Exarban classroom average temperature guesses.
So why are we looking at that column, but in the last slide we were looking at the far left column
So like
for significance? Like yes, so
Right.
SIG.
this is the significance for the Levine's test,
So what's the next one?
right? So this one just tells you whether or not you can keep reading this line.
Okay.
Once you get past here, here's all your significant stuff.
So what's different about what we're talking about in the next slide then?
So here's the same exact thing. So here's your Levine's test, and here's your significance level for that test. And if this test is not significant, it means that your variances are not significantly different, which is confusing, but it basically means you can go ahead and proceed with this test the way it is. So you kind of pass go here and go right into these.
And then that one's your
So that's like,
Right.
it's like step number 2. Step number 1 is we looked at what's SIG stand for?
Yep, significance.
Significance.
So step
So-
1,
So we looked at that first.
Yep.
And then it was not significant, which is what we like.
yep,
So we move on to two-tailed.
yes, exactly. So it's confused, like I kind of like to think of it as a little gate. Like I have to make everything very simple. So this is like the first road right here. And if it is not significant, you can go through this gate to read this row. If it is significant, you have to detour down to here and read this row. And so you don't even have to report anything about Levine's test. You just have to check it. You just have to see if it's okay for you to read this top line or if you have to read this bottom line. So it's annoying because, I mean, you spend a lot of time wrapping your head around this. But basically, if your Levine's test is not significant, pass go and just start reading this top line.
And you're looking at underneath the SIG, right?
Right, so here's the SIG.
Decide if it's significant or not.
Yep, so you can
So
see,
that's this point, I can't read this.
yeah, it's 0.990.
So that's over 0.05, so it is. So it is not significant.
Yes.
You just keep going.
Exactly.
Okay. If it was less than 0.05, then you would drop down. Okay.
That's exactly it.
And you would drop down and look at the two-tailed column,
Yep.
second number.
Down here, yep.
Okay.
That is exactly it. So the reason I have them kind of boxed off here like this for you is like this is totally different than this. This just lets you know if you can pass go. This is where your information
It's
is.
a different test.
It's a totally different test. Yep. So it's confusing because it's like there's a lot of little steps that if you don't know what you're doing, you could have totally different. What's interesting is your results wouldn't be totally different, but your degrees of freedom for your test would be different. So you'd be reporting a little bit of the wrong information.
So the ultimate answer that we're looking for
Right.
is this is not
Right.
significant.
Exactly, right here. So once you pass the Levine's test, so it helps you because you can see up here, this says Levine's test for equality of variance, and there's a line here. Like this is where Levine's test stops and where the t-test for equality of means starts. So everything in this part of the table has to do with how different your means are. And so,
And then that's when it's over.
yeah,
We found our answer. It is, let's see,
it's 0.09.
so it's not significant.
Exactly.
That's our answer.
So we went through all that to say the Exarban classroom and the Dundee classroom did not significantly have they didn't have significantly different guesses. Right? I know, you go through all of that. So yeah, that's the answer though. So it seems really hard, but once you see what this is, when we go through the output, when you do the lab tonight, you'll basically be clicking some boxes and you'll get this output and you'll say yes or no, these aren't different. The other thing to note here is this last orange box. 0 is included in the possible range of confidence intervals. So this last box is our confidence intervals, right? So we have a 95% confidence interval of the difference. So we're saying that the value we're looking for is the difference between the means. We are saying that the difference between the means can range from negative 1.09 to positive 12. So we're basically saying that we're 95% sure that the difference between Exarban and Dundee Classroom ranges from negative 1 to 12, right? That's the differences between them. Here's where I think it's kind of cool and it kind of blows my mind. But if 0 is in this range, which it is, right? Negative 1 to 12, 0 is in this range. So 0 is a possible value of the differences. That would mean there's no difference, right? So it's not a coincidence that the difference is not significant, because one of the possible differences is 0. You can, if you don't totally get that right now, that's okay, let it sit, because I finally got it now, 8 years after learning it. And I was like, oh, because a possible difference between Exarban and Dundee is 0, is nothing, no difference. If 0 wasn't in this, it would be significant. Yeah. And it's okay if you don't totally get that now, because like I said, I'm on year 8, and I was finally like, that's what they mean. Okay, I totally get it now. But anyway, just kind of a neat thing to know about confidence intervals. Okay, let's see.
Is 0 always included?
No.
No, not always.
Nope. So if it is significant, 0 won't be in there, because 0 is not a possible difference. They are significantly different, and then 0 wouldn't be in there. But the most important thing to know is the t and the significance, right? So our t value is 1.69 if we round up, and our significance level is 0.09, so it's not significant. There is no difference. There's no, and so you'd report it as there's no difference. And here we are. So we just did that whole test, and you would write up, there was no difference in temperature guesses between the Dundee and Exarban classes. And so the things that you need to include are, you want to include the means for both of those samples. I don't have that in the slides that you have, because I was looking over this and I was like, wait a second, we always have to report the means in there. So I can upload this tonight if you'd like to have a slide of it. But basically, you want to show your reader in text the difference between the means. So they'll see that these are slightly different, but they're not really different, right? The difference is probably due to random variability. It's not different enough to be meaningful. So you would write exactly this. There was no difference in temperature guesses between the Dundee, and then show them what the Dundee sample looked like. Their mean guess was this, the standard deviation was this. There was no difference between the guesses and the Exarban sample, and show them that. The mean of the Exarban sample guess was this, the standard deviation was this. So they can see everything you're talking about. And then you prove that there's no difference by putting your statistics in there. You put your t, your degrees of freedom, your t value, and your p value. And all of that stuff you get from right here, right? Your t value, your degrees of freedom, your p value, and here's your mean and your standard deviation for both of those groups. So all of the information will come from these two tables. Oops, there. All right. Good on that for right now? So the last thing to note for writing up results is basically everything. I just wrote them down in the slide so that you can see it all. I also included this line about the means, so you can see that too. I'll upload this after class. But basically, it's just walking you through exactly what we did. If you have a significant difference, make sure you compare the mean of a sample to another, the mean of the other sample, so you can say these are the differences. And you can say which one was higher or lower, right? So just kind of like you did with the one sample t-test. If there's no difference, say there's no difference, right? So don't say there's no statistically significant difference, just say there's no difference, and then you can report it. So yeah, and then again, little notes, specify what the samples are. Don't just say like, there was no difference in the samples. Like, what does that even mean? You want to say there's no difference in the Exarban and Dundee samples, and you want to mention what it is they do or do not differ on, right? Like, they don't differ in terms of average January temperature guesses, right? So you pack as much information into that statement as you can so that your reader knows exactly what you're talking about. Oh, I put that on there twice. Anyway, provide the mean and the standard deviation of the groups that significantly differ, and then you can see exactly how I would say it here. All right. Let's, so it's like 7:30. Let's go ahead and go through dependent samples because it's actually easier to understand than independent samples because you don't have any Levene's test stuff. And it's basically the same exact test, but instead of having two groups that you're comparing one group that you measured at two different times, right? So we're still comparing the difference between two means. It's just now we're looking at the mean of the sample the first time they took our test and the mean of the sample the second time they took our test. So because this is about the same test, you have similar variable constraints, right? So again, you see that the independent variable has to be a nominal variable with two groups, right? Like high or low, male or female, group A or B. And the other way we can kind of think of our groups is in terms of when they took the test, right? So these are still two mean differences. We're still comparing two means, but instead of it being two different groups, it's the pre-test versus the post-test, right? And so that's our independent variable because we think that when the group was measured will influence the dependent variable, right? So again, the DV has to be a scale variable, so it should have equal intervals, and this is the variable we think depends on the independent variable, right? So we think that your test score depends on when you were measured, right? Before you got the intervention or after you got the intervention. So we're still asking these same kinds of questions, but these dependent samples t-tests let us answer intervention types of questions like, does vacation influence productivity? That's the example your book gave, is how productive are people before they go on vacation and how productive are they after? So we're comparing the means of their productivity before and after. We can also answer questions like, does a smoking cessation intervention reduce the number of cigarettes that people smoke each day? Or does a reading program help students with their reading skills? So we can actually answer some of those types of things. And so these types of this dependent samples t-test, it's really most often used to compare the same group twice, right? Once before an event or an intervention and once after the event or the intervention. So if we are going to see if like a reading intervention influences reading scores, then you would measure reading abilities in children before the intervention. You'd get these pre-test scores for them, and that would give us a baseline, like how well are they reading initially. And then you'd give them the intervention, and then to see how well that intervention works, you measure their reading abilities after the intervention, right, in the post-test to see if their scores generally improve. So let's say here's our class. We basically have the peanuts, and we are measuring them once at the pre-test, and then we're measuring the same people again after the intervention. So that's what you can see here. And so let's say we did that. So here we have our two different scores, right? We have our different tests. So we see here's our pre-test scores, here's our post-test scores. And you can see we have the same sample, so our N always equals 12. And just by eyeballing these scores, the score before the test, you can see that the kids are generally doing a little bit worse, right? Their reading score is only 9.75. And after the intervention, we can see what their reading scores look like. So we can see that generally they kind of improve a little bit, right? Like they go from a 9.75 to an 11.75. So just like the independent samples t-test, we can see that there's a difference, right? We can see it right there. But this difference that we can see in our sample, is it actually like indicative of an actual difference that would exist in the population if they were to receive this intervention? Or is it just random fluctuation in the sample? So in other words, is this difference statistically significant? And that's where we have to go and do an actual dependent samples t-test to tell us whether this intervention actually works. So in this example, the independent variable is when the test was given, right? Was it given before the intervention or after the intervention? Because we think that when the test was given should influence their test scores, right? Pre or post. And the dependent variable is the test score. And so kind of putting this back in terms of our null hypothesis significance testing, our null hypothesis is that there is no significant difference, right? That the average pre-test score is similar to the average post-test score. That our reading intervention didn't do anything. So that's the null hypothesis, that it didn't work. The alternate hypothesis is that there is a significant difference, right? So that our average pretest score is significantly different from our average post-test score for our sample. That our reading intervention made a difference, a significant difference. So to answer this question, we again have to calculate a t-value, and this is similar to calculating the t-value for an independent samples t-test, except for instead of dividing by the standard error of the difference between the means, now we're dividing by the standard error of the differences between dependent means. So again, just like the standard error of the dependent, the difference between the means, this value just tells us the amount of error we can expect from repeatedly randomly selecting a sample and calculating the average difference in their pre or post-test scores. So again, this is just another one of those distributions of multiple pre and post-test difference scores. And so your book shows this two-step formula here that you can see right here for calculating the standard error of the difference between the dependent sample means. But I think you get the gist of this. We've done it like many, many times. It's very similar to calculating it for the independent samples t-test. And we're going to have SPSS calculate it for us anyway, so let's not calculate it. Let's just go ahead and move to interpreting SPSS output. But basically, like, you get it, right? Our t-value is comprised of looking at the difference between the average pre-test score and the average post-test score and dividing by the standard error for that statistic, for a dependent difference between dependent sample statistic. So it's just like all of our other t-tests, except for it's specific to this test. And what's great is SPSS calculates it for us. But basically the trend that you should be seeing is that every one of these t-tests has basically the same equation on top. The bottom just changes a little bit because we're getting a different type of standard error. All right, oops, sorry, there. So here is our output. And it looks very similar to the other output, right? So instead of having different groups, you have the same group and you have their pre-test score and their post-test score. So here's their mean, here's their standard deviation, here's the standard error of that mean. So here's all the group statistics. If you look down in this paired samples test box, you'll see the difference between the mean reported right here. So it even calculates it for you. It's like the mean decreased by 2 points. If that was positive, that would mean that it increased by 2 points. But it's basically saying, or I'm sorry, if it's negative, it means that it's basically just what was your first and second. But you can tell that it's a 2-point difference. So it was 9.75 before the test. After the test, it was 11.75. And so it got better, so it's negative. So sorry, it's the opposite of what I was saying. If it gets better, it's a negative. All this, right? Why are they, everything is just backwards. Anyway, you won't even really have to, like, care about that because you can look at the actual differences and you can say they got better by 2 points. So here's your differences. And so it's kind of cool because it's giving you this information that is like, you're trying to calculate the difference. So it's giving you the mean difference, it's giving you the standard deviation of the difference, and it's giving you the standard error of the differences. So these are all the pieces you would need to do, like, here's all of this information, right? The difference between the means and the standard error of that. It's all right here. So in case you wanted to calculate it on your own, you totally could, but SPSS has already done that for you. So you can look right over here. Here is where all the information you want to see is. So here's your t-value that was calculated using this formula. Here's your t-value. It's a negative 2.671. And that's a pretty high t-value. Here's your degrees of freedom. These are also calculated slightly differently. So you can see down here the degrees of freedom for a dependent samples t-test is the number of pairs minus 1. So we have 12 pairs, right? We have 12 people here. So we have 12 pairs. So 12 minus 1 is 11. So that's how it calculates that degrees of freedom. But so if we were to look at our table of t-values, we'd see that a t-value associated with 11 degrees of freedom and a significance level of less than 0.05 would be associated. This t-value is bigger than that cutoff. But so basically when you're looking, you can see here's your t-value, here's your degrees of freedom, and here's your significance level. So if we look at this, our significance level is 0.02. So it is significant.
And is this one where we don't want it to be significant?
We do want it to be
Oh my
significant.
gosh.
Yep. So there's no Levine's test anymore. That's gone. This is telling you. See, and luckily, so you should see on here, it says p-value for t-test.
So the dependent samples, we do want significance with that number. With the independent, we do not want significance.
Well, we always want significance for the t-value.
Significance for the t-value.
Right. So like even let me scroll back here a little bit. So here was our independent samples t-test. Here's our p-value for our t-test. And we want that to be significant because that means we can support our alternative hypothesis. It means that they are different. And usually we want them to be different because we're trying to say, hey, this matters. This makes our groups different.
So why were we saying over and over again, we don't want them to be significant?
So that's this Levine's test for equality of variances.
Okay, so the part number 1, we don't want it to be significant.
Exactly.
Once we get to the t-test.
Yes, you want it to be significant. So you'll see that's why I have the orange box that says p-value for t-test. That's the one you want to be significant. So this is where it's a little tricky. So maybe write this down, note this. For the independent samples t-test, when we're comparing two different groups like Exarban and Dundee classrooms, for the independent samples t-test, you have this equality of variances assumptions that has to be met. So we have to test for it. And you don't want that to be significant. Because it would suggest that the equality, that our variances, our equal variances assumption has not been met. So our test is...
So if it's not significant, it has met the assumption?
Exactly. So it's backwards. But, so...
You want it to meet the assumption, sorry.
Yeah.
So the first section, the equality of variance, you don't want it to be, that way you can keep going down the line.
Right.
Because if it is, then you just drop down to the second one.
Right. So honestly, it's okay if it is significant because SPSS already corrected for it anyway. But if you just need to know which row to report the results from. And you want it to not be significant because that's the assumption of the test. It basically means that your results are probably more stable, more reliable, more accurate. So it's weird. So again, remember this. This is independent samples t-test. When we are comparing two different groups, right? In an independent samples t-test, you have to meet this equality of variances assumption, and if you don't, you have to correct for it. And so your first thing is to look at that box. And then, based on the information in this box, you know which row to look at in this box, right? That's only for the independent samples t-test. So let's go ahead and scroll back down to the dependent samples t-test output. You'll see there's no Levine's test for this one. They don't even have it because the idea is that you're measuring the same sample twice. So you should have the same number of people in it, and they should have similar variability because they're the same people.
Right.
So you don't even, they're like, that assumption doesn't even have to be met. That's not even an issue. We don't even look at it at all. So in the dependent samples t-test, when we're measuring the same people pre and post, we don't even have a Levine's test. It's not even an assumption. It doesn't matter. So you don't have to look for that box or anything. In fact, you can kind of ignore all of this stuff. And you can go right over here, see where all the orange arrows are. Whereas here is your t-value for that difference between the pre and post test. And here's the degrees of freedom. Here's your significance. So since this t-value is significant, it's telling you that the means for the pre and post test are significantly different. So our values of 9.75 and 11.75, this is a significant and meaningful difference. Well, meaningful depends on what you want, but it's a significant difference. So let's say that we gave this reading intervention and we wanted to see if it worked. So we measured these kids on how good their reading was before the test, and they gave a 9.75. So we'll just pretend that this test ranges from 1 to 15. That's a moderate score. Then we gave them an intervention where we taught them how to read better. That's really lame, but we just made them read better in our intervention. And we wanted to see if it worked. Whatever we were doing in the intervention, we wanted to see if it worked. So we measured them later, after we gave them the intervention, and we see that the mean is 11.75 now. So this group has gone up in points, right, after. So now their test is, they're 2 points higher. They've done 2 points better. So whatever intervention we gave them, it did increase. It made their reading scores better. And the big question then is, was it significantly better? And we did the test, and yes, it is, because the t-value is associated with the significance. That's a p-value that's less than 0.05.
Because there was a difference.
Because there was a significant difference. Yep.
So if it was greater than 0.05,
Right.
we would say there was no difference.
Yep.
And it wasn't really reliable.
Exactly.
Okay.
That's exactly it. You would say that, you would basically say there's no difference and you just don't have enough support that your intervention works. You're like, yeah, it made a little bit of a difference, but, so like, that would probably happen if this mean was 9.75 and the post-test mean was like 10. You could say, oh, it increased, but probably not enough to say that this is worth spending money on and implementing in the school system. Before you do that, you want to make sure this has a significant effect on kids' reading. All right, let's see. And here, let's just bend our minds a tiny bit more really quickly. And this is this orange box here. So here is our confidence intervals. And what this is saying is that we are 95% sure that the difference between our pre and post test scores, so the difference score, this difference of 2, this difference between our pre and post test scores ranges from -3 to -0.35, which is really confusing and doesn't really make that much sense. But the most important thing to notice is that in this range is 0 in this. No. So a different score between pre and post test, a different score of 0 is not something we would be 95% sure happens. So it's outside of our confidence interval. It is not a value we think could happen given our sample, and so that corresponds with this being significant. So 0 is not a possible value. We're 95% sure 0 is not an option. And so it is significant. Because 0 is not in there. We're 95% sure that a difference of 0 between pre and post test scores is not an option. All right, so let's go ahead and look at, so this is how we would write it up. Same exact way that you would write up an independent samples t-test, except for now you interpret your findings just slightly different, right? So post-test scores, go ahead and, post-test scores were significantly higher than pre-test scores. So I put the post-test scores in here to show them, like, hey, in the post-test, they went up to 11.75 with this variability around the score. So post-test scores were significantly higher, because they were higher, than pre-test scores, right? And then I say, here's the pre-test scores, you can see it yourself. And then I prove it with my t. So here's my t value, 11 degrees of freedom. Or yeah, my t, here's the actual t value, and here is my p value. So you can say p equals 0.02 like it shows in there, or you could say p is less than 0.05, however you want to say it. So in terms of our null hypothesis significance testing, we basically can reject the null hypothesis, right? And we have support for our alternate hypothesis, which is that the pretest mean is not the same as the post-test mean. Right? They're different. It's a lot of like twisting. So the last thing, the same thing, when you're writing up, here's all your little rules. You know, if there is a significant difference, compare the mean of one sample or one mean to the mean of the other one, and that will tell you the direction of difference, right? So like if we were doing a weight loss intervention, success would be measured by decreasing scores. So you'd say something like the pre-test scores are significantly higher than the post-test, or the post-test scores are significantly lower, indicating that people using this intervention lost weight. So it all depends on the difference between the pre and post-test scores, right, and how you interpret this. But you want to keep that, you want to put that in your statement. You also want to specify what the samples are, what the variables are, and provide the mean and the standard deviation of the groups to show them. And so that's exactly how you would write it up. And if it's not significant, you would just say it's not different, and you would report those results if you want to. All right. It is like 7:50. Let's see what we can do. It's like, I'm sure you guys want to dive into ANOVA. All right, just a couple things before we even consider doing ANOVA. Let's see. So our t-test has some assumptions. We talked about the assumptions of the dependent and the independent variables, right? Our independent variable has to be groups, or, you know, a categorical variable that has two levels. Our independent variable our dependent variable has to be some kind of a scale, right? It should be some kind of a scale variable. But we should also mention that we also assume a normal distribution of our scores like we do with everything else. And we also know that if we don't have a normal distribution, a lot of our probability assumptions fail. They just don't work as well, right? They're not meant to apply to a non-normal distribution. But it's okay if you do have a non-normal distribution, or if you have an ordinal dependent variable instead of a nominal one, because you can use what's called non-parametric stats. We're not going to dive into these, but they're written here in case you ever need to look it up. So basically what you'll see is that all of the types of stats we're doing fall under this parametric statistic column. So we have our scale dependent variable, we have a normal distribution, and so we can use parametric statistics. So we can do our one sample t-test, our independent sample t-test, and our dependent sample t-test. But if you didn't have these things, if you had an ordinal dependent variable, so your dependent variable wasn't like temperature or height or weight or something like that. What if it was like a rank order or a survey, right? Ranking from 1 to 5. If you had that kind of variable, you could do a test like this. Or if you had a non-normal distribution, you could do a test like this. You would just have to look up these non-parametric. Oh, Alicia. Statistics. Come back. Oh my gosh. Okay, good. And we won't go over them, but there they are. So if you wanted to do something like a one sample t-test with an ordinal variable or a non-normal distribution, you'd use this Wilcoxon test. If you want to do an independent samples t-test and you're violating these assumptions, you can use this Mann-Whitney U test. And I don't think your book really goes into them, but if you wanted to look them up, if you're on the job or something, we could do that. So just to kind of review, we went through a lot of different types of t-tests. So let's just talk about all the ones we did. We did the one sample t-test, and this is where we want to compare. We didn't do it today, we did it last time. This is where we want to compare our sample against a known value, like a population mean or something like that. And we did this last class when we talked about shoe size and Omaha women's shoe size and comparing our sample of Omaha women to see if our shoe size was significantly different. And then today we kind of extended this. We looked at independent samples t-tests. And this is when we want to compare the means of independent groups, right? We did this today when we compared the classroom of Exarban kids with the classroom of Dundee kids. So we looked at that and we looked at how their average guesses of average January Omaha temperature, see if their guesses were significantly different, and they weren't. And then lastly, we did this dependent samples t-test, and we use that when we want to compare means of the same sample measured at different times, right? So we did this when we looked at the effects of our reading intervention, how our intervention affects the scores. So we looked at their pre-test scores, how they were reading before the intervention, and we compared it to post-intervention reading scores. And we saw that our intervention did significantly increase these scores. All right, do you guys want to take like a 5-minute break? And we'll see what we can do with one-way ANOVAs, which are an extension. But we'll just come back at 8. Is it 7:55? And we'll do what we can. Let me see. Oh, there. All right, take it away. We're back. We are moving on from ANOVA. We are not going to do it tonight. We're going to do it next time. And so we're just going to skip to the lab. So we're at Angel, and I'm going to lessons. And I like treating Tegrity as if they're a person I'm talking to. Like, hi, Tegrity. Here we are now. So we're going to labs, and we're going to, oh, yeah. Is there answers on there?
No, I said integrity answer.
Oh, yeah. Then I'm like, oh, it has been too long. I can't do that, Dave. Okay, so here's our Lab 3 PowerPoint, which will walk us through everything we're going to do, except for the end. So I'll repost, I'll repost this lab without ANOVA stuff. So just ignore the ANOVA stuff. But there's the lab. And if we go back to lessons and labs, we'll get the Lab 3 data set. All right. Yeah, it's okay. So it's kind of like real life. Actually, it's not like real life, right? There'd be one more woman. But anyway, so there's your, let me get my little lab out so I can better instruct you, anticipate what we have to do next. Something in this room. So, if you look at the lab, just to, where'd it go now? Oh, here, there. Oh, that is not it, Alicia. There, okay. So, the first thing that we're going to do is an independent samples t-test. So, we're basically going to do an independent samples t-test, and then we'll do a dependent samples t-test. So, our independent t-test, to do it, your data has to look a little different than what it does look like. So we have to transform it a little bit. So it looks like this. There. You can see that now. This is what it looks like. But what we need to do is put it all in one column. So what you need, we'll skip down here, but basically you need a height column and a gender column, because that's how SPSS understands it. So to do that, I think the easiest thing to do is to put men by all of these men. So you'll have this column. You can name it gender if you want. And then all these men's height. And you can copy it and paste it. think you can actually drag it. Yeah. Did you guys see that? I'll do it again. Okay, so if you type in men, and now you got the little black box here, and there's like a little corner. If you grab that corner and pull it all the way down, it autofills it, right? Save us all some time. What's that? What? Why is this yellow?
I just copied and pasted it and we'll have like 4 or 5.
So once you've done that, then I would go ahead and write women and copy these women's heights. Oh, you're in, oh yes, I'm in Excel. You're like, no, what? Why is it not? That's what, so the little lab thing says, do it in Excel because Excel is much more user friendly than SPSS. So then I would copy women's height and put it underneath men's height and paste it. Let me zoom out a little bit more. And then once you type in women right here, you can drag it down too, so you don't have to keep writing it over and over again. There. I would also maybe copy this whole thing, all the heights, and put them over into this column so it doesn't say men's height, and you could just write height on the top. All right. Wait and make sure everybody's got that done. Okay. All right, does everybody have the gender and height columns done? Let me put these in order. Insert. Why did I just do that? Anyway. Okay, so then the next thing I do is go ahead and copy height. Like that, copy that column. Oh, and open SPSS. I don't think I've done that just yet. Sorry, let me open SPSS. It should probably let me go to course. What's it under again, you guys?
Your apps.
My apps. Where's that at?
It's on the
Oh, thank you. Home.
or the My CSM page.
There you go.
Oh, right here. Thank you, guys. You tech-savvy generation, you.
I have an email. Did you see that? That's where your email is.
That's... I do have an email. I'm assuming it's probably an assignment. It's like, oh, to do those tonight. Okay, so after you've got your Excel file, right? So you want to have one gender column and one height column. Only because that's the way SPSS is going to be able to analyze it. So once you've got them organized like that, go ahead and open SPSS. Cool. And paste it in there.
Does it matter which side is on which side?
No, I don't think so. Now, maybe if I can. Do I have to do it not in. I have to use not Google Chrome, huh? All right, sorry. It's still setting up my SPSS. Yeah, okay. There, yay, okay. Yeah, so if you want to paste them in like this, paste in the data view. So you'll see data view there. And you can either right click and paste, or you can do Control V. Oh, you also don't want to paste in that little height. So if it pastes in there, click on that and right click and say clear. You don't want to paste that in there. So paste in height first and then go back to your Excel file and then paste in gender. Right here. All right, everybody got those pasted in? Awesome. Okay, now go to variable view and we're going to name them, right? So you want to name the first one height, H-E-I-G-H-T, and the next one we're going to name gender. And we're going to change, height to numeric. So it's a string, but we want to change it to numeric.
Heights, change it to numeric.
Yep, and then looks like we want the width to be 8, but I don't think it matters. And we want it to have 2 decimals.
Why won't it let me type in the gender?
Oh, weird. Let me see.
Okay, so you try typing names? Oh, okay, so you have to paste. Yeah, well, I copied that like 3 times. Okay.
Does she have duplicates like we? Trying to type the same word twice.
I deleted it all because you have that other column.
Now he just beat it, right?
Yep,
Isn't
yep.
that always?
Magic
It's like, I'll just stand here. It'll work.
Okay.
All right. So yes, in the variable view tab, you want to name your first variable height. You want to name your second variable gender, and you want to change the properties of your first height variable, right? So we're making it was string. We're changing it to numeric. So to do that, you just click, and you'll see that numeric is like the top option. And go ahead and click OK. And you want it to have 2 decimal places because our height in our Excel file has decimals. And way over here on measure, height is not nominal, right? It's scale. So let's go ahead and change it to scale. But gender is nominal. We can keep that there. All right, so now that we've done that, we can go back to our data view, and you should see now it says height at the top, says gender. Your height variables have decimal places. But I'm not really sure why we want them to have decimals because they don't have any decimals behind them. But anyway, there we are, in case. So what we want to do is an independent samples t-test, right? We want to see, basically we want to see if height depends on gender, right? So do men and women have significantly different levels of height? So we're comparing a group of men with a group of women, and we want to see what their means are, what their average height is, and see if it's significantly different. So to do that, we go to Analyze, and you'll see there's a Compare Means option. And when you compare means, you can see we have all these different options. You have your one sample t-test we did last time. Here's our independent samples t-test. So you want to choose that. And when you click that, you'll see you have your dialog box pop up. And you want to put your test variable in this box. So your test variable is what you think varies. It's your independent variable. So in this case, it's height. We think height. Wait, that's our dependent variable, right? No, height. Thank you. Yes, height. Goes back and forth in your head all day. Okay, and then our grouping variable is gender, right? Those are the groups we want to look at. And so go ahead and select it and put it into this grouping variable box. And as soon as you get this grouping variable, you put it in there and it has all these little question marks. So you want to define your groups. So click on Define Groups, and you'll see there's an option for you to define your group 1 and group 2. So we'll say group 1 is men and group 2 is women. And you just have to make sure that you type in your group definitions the same exact way they are in your data set. So if this said man and woman, you would have to type in man and woman. Otherwise, SPSS won't know what you're talking about. So once you do that, go ahead and press OK. And you'll see my groups are defined now. Gender, men, women. The next thing I want to do is go to options. So if you click on options, this is where you'll get your confidence intervals. So it says right here, confidence interval percentage. And you can set it at whatever you want it to be. 95 is pretty standard, but if you wanted to do 99, you could throw that in there and it would do it. So that's ready. You can press OK. And then you can press OK here. And you'll see the output of your t-test. So this is exactly what we went over in class, right? So this is an independent samples t-test. So we have our Levines. It's the first thing you see here, right, in this. So first up here you see you've got your gender, and you've got men and women and how they vary in height. So here's the average men's height. It's probably 68 inches. Women is 64 inches average. Here's the standard deviation, standard mean. You can see that we have 15 men and 14 women. So here's our descriptives. This is our group statistics. This describes our groups. And then we can go down here to the independent samples t-test box. And you can see the first thing is that Levine's test, because one of the assumptions of the independent samples t-test is that our groups have equal variability. And let's just look really quick. Here's the variability for our groups. Men's vary, their variance is about, their standard deviation is 2.65. Women's is 3.55. Not wildly different. They're probably pretty similar. So let's go ahead and look at Levine's test, and it is not significant. So we have met this assumption. Our equal variances are, our assumption is met. We have equal variances. They're not significantly different. So we can pass go and read the top line. So at the top line, right, so you want to look at your, here's your t-test for your, so here's, yeah, your t-statistic. Here's the significance for your t-test. This is the one you really care about. And so you can see, if you want to interpret this, you've got your, our p-value is 0.009. So that means it's significant. Cool. So basically what we're saying is that men and women's height, our sample of men and women, their height is significantly different. And if we wanted to interpret that, we can look up here and we can say that men are significantly taller than women, right? Because their sample mean is higher. So when you'd write it up, that's what you would do. You would say that men in our sample were significantly higher than the group of women in our sample, or taller. Sorry, higher. That sounds weird. So that's where you get all of these values. All right, any questions about this? All right, let's move on to dependent samples t-test. So let's go here. Yeah, this one. Did all these things in case you want to follow along on here. Okay. So for our dependent samples t-test, our data has to look, so here's our Excel file, right? If you look at the bottom of the Excel file, you'll see multiple tabs. So we just did the height data. Now we're going to move on to the ACT data. So
Should we get rid of this altogether?
you can just keep it. It's weird, but yeah, you can either delete it or you can keep it. It really doesn't matter.
Oh, I'm so sorry. Where did that come from?
Yeah, that's okay. Okay, so if you leave your SPSS and go back to your Excel spreadsheet, you'll look at the bottom and there's different tabs. And so this second tab is ACT data. And basically what we want to see is we're looking at how these students performed on their ACTs when they were juniors and then when they took it again when they were seniors. So we want to see if their scores differ. So it's a dependent sample because we're measuring the same people, right? We're measuring these kids while they're juniors and we're measuring them again when they're seniors. We just want to see if when they took the test, influences their score. Did they do better when they were younger? Did they do better when they were older? So to do that, we basically want to copy this as is into SPSS. So we want to keep them separate. We don't want to combine the columns. So if you want, you can highlight all of it in Excel, copy it, go back to your SPSS, and just paste it in. So I can paste it over here, yeah. Sorry. All right, so if
So
you,
you want us to leave height and gender?
you can leave it, you can delete it if you want.
I did, I just did like the different thing, we skipped one.
Oh yeah, you did, yeah, that's okay too. Basically, you're going to tell SPSS what variables you want to analyze. So as long as you don't bring height and gender into this, it won't influence your results. Yeah. All right, so you want to do kind of the same thing, right? You want to copy this in here, and then you want to name your variables. So you can go to variable view, and our first variable now is going to be ACT Junior. So we do ACT, just did that. And then the other one is ACT Senior. And these are already both numeric, so that's nice. We don't have to change that. The only thing we want to change is our measure is not unknown. These are scale. All right. So once we've done that, you can click back into data view and you can see now you've got your variables all named and ready to go. All right, so if we want to do a dependent samples t-test, we kind of do the same thing. You go to analyze, you go to compare means, and it doesn't say dependent samples, it says paired samples t-test, but that's your dependent samples t-test. So if you click on that, you get this really different looking dialog box, right? It's different than all the other ones we've seen. But you want to tell it, if you select ACT Junior and click it over, it will change the way the whole box looks, right? Like it changes the options you have there. So you want to click that in there and you want to select ACT Senior and put that in this one, variable 2. All right, everybody following along so far?
For some reason, instead of the little
Ruler?
ruler, I'm seeing a graph, like a bar graph.
That's because I bet your variable level is nominal. So to get rid of that, let's go ahead and close this. Go to your variable view.
Oh, you're right. Yeah,
Yep.
Sorry.
And change your measure to scale. Nice. I can go right back to this. Oh, that's not it. Never mind. Analyze, paired samples. Throw these in here. All right, once you've got these all in here like this, go to options. And you'll see here's our 95% confidence interval. I was having you click on it so that you can see it. It's already ready for you to go. But anyway, so there's that. And then you can just click OK. And you'll see here's your t-test. And here's exactly, except for this paired samples correlation, which you can ignore. But here's our statistics, right? So, let me get that up here. So, here's our mean for when they took it their junior year. And you can see the average ACT score was 19. That's our 12 students. Here's the standard deviations. Here's the ACT scores when they were seniors. Not a ton higher, but 1 point higher. They went up about 1 point. And if you look down here at this bottom, you'll see here's the difference between the means, because that's what we're looking for. We see that it increased a little over 1 point. And what you're really interested in is the t-value, right? So our t-value is negative 3.386. Is it significant? Yes, it is, right? It's less than 0.05. So this is saying that even though it's only 1 point, there is a significant difference between ACT scores the junior year and ACT scores the senior year. And when we interpret that and write it up, you say that the post-test score or ACT scores for their senior year were significantly higher than ACT scores the first year they took it, their junior year, right?
Why are we looking at the T? Why aren't we looking at the T scale?
Oh, this right here.
So I'm sorry. I
Yep.
thought you said the T. Okay.
So the T value is like your ratio of, I don't know if you want to know this, but it's your ratio of your differences between means to your standard error, basically. But so you get this T value and you want to see if it's significant. So when you're reporting it, when you're writing it up, you do report the T value, but you say whether or not it's significant. And it is significant, so that's what you would write up. Are there any questions about that?
Now, when you write it up, you say the post-test for the CP or ACT
Yes.
junior year was significantly higher. Do we have to put those numbers behind it too, just like we were doing with other?
Yep, that's what I would do. Is so you'd put the mean. So you'd say post-test parentheses
The means.
right here. So remember, this is your post-test.
Okay.
It's the second one, right?
Okay.
Yep. Then you put the mean, and here's your standard deviation right here.
Okay.
So put the mean and standard deviation, and then the only things you need from this table are your T, your degrees of freedom, and your significance. All right. And we will save the ANOVA for next time.
This is our lab right now.
So and that's, we're done.
I thought the first day I kind of was able to save my lab, but this time I've been having some problems.
Oh, doing it on here? I'm going to go ahead and turn this off there. Bye, Tig.